Okay, so we have this notion of a quadratic form, and the idea is that quadratic forms are represented by symmetric matrices. Now, what we want to do is classify quadratic forms. And quadratic forms are classified according to their definiteness. Well, what definiteness does is tells us the signs that the quadratic form takes on when we plug in input vectors that aren't equal to the zero vector. So when we plug in the zero vector, we'll always get 0 as the output. So the question is, what might we get if we don't plug in the zero vector? Well, we call the quadratic form positive definite if the quadratic form is always positive, again, when we don't plug in the zero vector. We call a quadratic form positive semi-definite if we know that it is always non-negative. On the other hand, we call a quadratic form negative definite if it is always strictly less than 0, again, away from the origin. And we call the quadratic form negative semi-definite if it is always non-positive. So the last category of quadratic form is the category of indefinite quadratic forms. These are the quadratic forms that both take on positive and negative values. So every quadratic form fits into at least one of these 5 categories. One important thing to point out is that everything that is positive definite is also positive semi-definite, and everything that is negative definite is also negative semi-definite. So quadratic forms can fit into more than one of these 5 categories, but they can't fit into all of the 5 categories. Okay, great. So the idea here is that these terms are also used to classify real symmetric matrices. Quadratic form is represented by a real symmetric matrix. So whatever definiteness that quadratic form has is the definiteness that we say that the symmetric matrix has. So let's look at some examples here. Our first example is the quadratic form on 2 variables given by x squared plus y squared. Well, as long as I don't plug in the origin, this is always greater than 0. So this means that this quadratic form is positive definite. And remember, everything that is positive definite is also positive semi-definite. Easy enough. What about our second example here? This is the quadratic form given by x squared minus y squared. Well, if we think about it, if I plug in like 1 comma 0 here, the output will be 1. But if I plug in 0 comma 1, the output will be negative 1. So this quadratic form takes on positive and negative values. This means that this quadratic form is indefinite. It's positive for some inputs and negative for some other inputs. So this quadratic form is indefinite. Here's another example. This one is q of xy equals x squared plus 2xy plus y squared. Well, this one's a little bit more difficult to see, but if we stare hard enough, we might get lucky and realize that this actually factors as quantity x plus y squared. And the thing here is that the quantity x plus y squared is always non-negative. This is greater than or equal to 0, which means that this quadratic form is positive semi-definite. However, it is not positive definite because it is certainly possible for this quadratic form to equal 0 when we don't plug in the origin. If y equals negative x, this will always equal 0. So this is an example of a positive semi-definite quadratic form that is not positive definite. So far, like for these quadratic forms, we can sort of look at it and then perhaps infer the definiteness. But then we get to something that looks like this. 9x squared minus 32xy plus 10xz, so on and so forth. This one's much harder to work with. And in fact, I have no clue what the definiteness is here. The point is, it's not always easy to see what the definiteness is. So finding definiteness is hard. So what we want to do now is we want to sort of attack this problem of being able to find the definiteness of any quadratic form. Well, our first step in this direction is this theorem that tells us about gramians. Remember that the gramian of any matrix is always a real symmetric matrix. And it turns out, according to this theorem, that the gramian is always a positive semi-definite matrix. And the proof here is not terribly difficult. If I look at the quadratic form represented by a Gramian, the formula would be q of vector x equals the inner product of vector x with A transpose times A times vector x. And now we can take advantage of the adjoint formula. We can move this A transpose on the right-hand side of this inner product to the left-hand side, but when we do that, we have to transpose. So now we're looking at the inner product of A times x with itself. And remember, the inner product of any vector with itself is its length squared. So this quadratic form is equal to the length of A times vector x squared, which is guaranteed to be non-negative, which is what it means for the quadratic form to be positive semi-definite. Great. So that's the proof of our theorem. Let's look at an example here. So here, we're looking at the quadratic form represented by the real symmetric matrix S, and the idea is that S here is the Gramian of this matrix A. Well, as soon as I know that S is the Gramian of A, I know that my quadratic form here is positive semi-definite. In our proof of the theorem, we actually had a formula for that quadratic form represented as a Gramian that's nicer than the general quadratic form. Here, the quadratic form is the length squared of A multiplied by the variable vector. So this quadratic form is quantity 3x minus 5y plus 9z squared plus quantity 2x plus 7y plus 6z squared. The first term here is what we get when we take an inner product of the first row of A with the variable vector. And the second term here is what we get when we take an inner product of the second row of A with the variable vector. So the idea is that the sum of these two squares is the length of A times x squared. Now, this is positive semi-definite, being the sum of squares. But it's also worth pointing out that this is, even though this is positive semi-definite, it is not positive definite, because the rank of S here is the rank of A, which is 2, which is less than 3. What that means is that there are certainly vectors I could multiply S by that would produce the 0 vector here. So it's possible for this quadratic form to equal 0 without plugging in x equals 0. But we do know that this will always be greater than or equal to 0, so this will never be less than 0.